Okay, good morning, gang. So, sorry, this 8 a.m. stuff is challenging for me too. We'll go ahead and get QCam fired up and get everything connected and we can get started. Just one more second. I'd like to begin today by looking at a handful of homework problems, try to get a feel for how comfy you guys are with these. And then there is one more concept that we have to introduce this week, one more little section to cover, but it's a very easy section. I don't think you'll find it intimidating at all. Come on, come on. All right, there we go. That's good. Sweet. All right, so I'll go ahead and switch over to the .cam. See that? Let me do that. All right. Oh, sorry. There we go. So today we're going to work some homework problems, and we're going to talk about section 6.5, which is on average value. Trying to think if there's anything else that we urgently needed to talk about. I don't believe that there is. No. No, I think that's it. All right. So then we can begin working some of these problems, right? Trying to make sure everybody's comfy with the sort of thing that we've been doing in class lately. And I would like to take requests from you guys. So of the current homework problems, which ones are you most intimidated by? Which one would you most like to see?
We do number 11.
Sure. Yeah, this is a good one. Does anybody have any ideas as to how we could get started with this? Does this remind anybody of anything?
I think, can we rewrite the x to the 12th as x to the 6th squared?
Good, yeah, that's the magic here. This kind of looks like the arctan integral. And the x to the 5 upstairs is exactly what you would need to group with the dx in order to substitute u equals x to the 6. So maybe I would write this one last time as 1 over 1 plus x to the 6 squared times x to the 5 dx, like that, before actually making the substitution. And this looks like an arctan thing, right? 1 over 1 plus u squared is arctan u. Kitty cat, you can't be like that, buddy. Sorry. All right. So from here, we would want to make the substitution u equals x to the 6. Right? Somebody mentioned that in chat. Yeah, that's exactly correct. Okay. Because when I differentiate this, I'll have my x to the 5 piece that I need. And also, this will become very, very nice. So here's du. Du would be 6x to the 5 dx. And since it's an indefinite integral, I don't need to worry about changing any bounds. There are no bounds to change. But you might consider rewriting this as 1/6 du equals x to the 5 dx. Some people prefer to solve this line for dx and then plug that in. That's okay. Just make sure all the x's go away before you move to your next step. I prefer to write it like this. I prefer to try and identify the piece that I have and then see what that is in terms of du. So this will be 1 over 1 plus u squared times du over 6, or 1/6 there. I can pop the 1/6 out front, actually. Let's go ahead and just do that. So this 1/6 is the 1/6 from my differential. And what's left over is the integral of 1 over 1 plus u squared. And that's arctan. What's the inverse tangent? And then the last step here, just because this is an indefinite integral, no bounds, we're not evaluating, so we tack on our plus c, and we have to go back to the original variable. So that is 1/6 times the inverse tangent of x to the 6 plus c. And you can imagine differentiating this, right? The c would differentiate to 0. And then if you went to differentiate this piece would come along for the ride, and this guy would differentiate to 1 over 1 plus whatever this is squared. That's the 1 over 1 plus x to the 12. And then by the chain rule, you would have to multiply by the derivative of the inside. Well, the derivative of the inside is 6x to the 5. The 6 and the 1/6 would cancel, and then that would give you your x to the 5. So you can always check your work on these indefinite integrals just by differentiating your answer and seeing if you get the thing you started with. And here we do. Questions on this? That's Any questions on how we did this, or any one of these steps? Did anybody try anything different? Nala. Nova. Anyway, what other homework problems would we like to look at? I think we have time for 2, maybe 3 more. What else would we like to see? What else is feeling intimidating as we work through these? Zach said he'd like to take a look at 18. Yeah, this is a good one. All right. So this is a 6.1 problem. It's an area between curve problem. I'll do my best to draw it well, though I am no artist. All right. So here's our first parabola. It's the blue guy. We're going to pretend like this goes through the origin because it's supposed to. Just really big points. And the red guy is also supposed to go through there. He's hanging out like, I'm going to exaggerate him a little bit. He's hanging out like this. Okay. So we'll call this one, this is x equals y squared, y minus y squared. And this guy is x equals y squared minus 4y. And the area we want is this area. Okay. So what do we do here? Can I set this up as a dx integral, or is this going to be a dy integral? Is there a clean way to represent either of these curves as functions of x? Yeah, both Juan and Rakib got it right in chat there. That's definitely going to have to be a dy thing. I have to think of my little Riemann rectangles as going side to side like this rather than up and down. Because neither of these guys are functions of x, but they are both nice clean functions of y. So that means I'm going to integrate my rightmost function, this guy, minus my leftmost function, this guy, from whatever this y value is, and that one we know is 0, up to whatever this y value is. So before we can set this up, we have to find the intersection points. Oh, Rakib seems to say that they give us that intersection. Is that the case? Yeah, this looks like the origin. I was thinking they might be giving us the vertex there, but I think you're right because this is the point that they've got filled in. So it does look like they've given us that point. So these are 0, 0 and negative 15/4, 5 halves. So they've saved us some time there. That's nice. And then like Rakib said in chat, we have to remember that these are y values. Because our integral is running dy, we imagine this little strip as sweeping up and down through this region from whatever this y value is, which is 0, to whatever this y value is, which is 5 halves. So the integral will run from 0 to 5 halves. And it will be the right minus the left. And it will be a dy integral. The rightmost function is y minus y squared. The leftmost function is y squared minus 4y. And when you subtract chunks like this, remember to put them in parentheses. So that's going to be the integral from 0 to 5 halves of y minus y squared minus y squared minus 4y. And don't leave off your dy's. Make sure you're careful with all the notation. The big parentheses around the outside of the integrand, this and this, are not as important as these, the little parentheses inside, but it's just good notation. So not forgetting to write those, not forgetting to write the dy, not getting lazy and skipping writing bounds, that sort of stuff is important. one of the things that we try to do in the beginning of this class is train you on good notation. That way, when you get to the middle part of the class where it's really necessary, you've already built good habits. So I encourage you, as you solve these, please try to make your solutions look like mine. Try to make them look nice and neat as much as you can. I know mine's not perfect, but do your best to keep things neat and organized. We'll go ahead and distribute this negative and clean up, combining any like terms we have. Here I've got negative y squared, and then when I distribute this negative, I'll have another minus y squared, so that'll be minus 2 y squared. And then linear terms, I have a y here, minus 4y, so that's going to be y plus 5y, so that'll be plus 6y, and there are no constant terms, that's everything, so it's just that dy. Now this is a polynomial, so I can just use my power rule. The negative 2 will come along for a ride, and an antiderivative for y squared is y cubed over 3. So this will be negative 2/3 y cubed. And the 6 will come along here. Antiderivative for y is 1/2 y squared. 6 times 1/2 is 3. So that'll be 3y squared. And we're going to evaluate that between these two bounds. So from 0 to 5/2. Well, I have 1y here. Oh, it should be 5 plus 4y. Yeah, I'm sorry, this should be 5y. 5y. Getting ahead of myself. So then this will be 5/2. Yeah, thank you, thank you. Yes, you're correct. You're correct. We have the 1 here, and then plus 4 more here makes 5, not 6. I don't know what I'm thinking. And then this will be a square. Yeah. Sorry, still a little bit of sleep. I appreciate you watching carefully. Yes, thank you. Thank you, sorry. Okay, this is sound now. This will definitely be the negative 2/3 y cubed. And this is a 5y, so the y will integrate to y squared over 2, and we'll have 5/2. Yeah, okay, this is okay. Very, very sorry, thank you. So when I evaluate this at 5/2, we'll have negative 2/3 times 5/2 cubed plus 5/2 times 5/2 squared. And when we evaluate at 0, we'll get 0. So this is all plugging 0 in for y into both of these definitely gives 0. This is 5/2 cubed, so we can try to treat this as negative 2/3 times 5/2 cubed plus 5/2 cubed. And I think the fastest way to simplify this is going to be to factor a 5/2 cubed out. So give me just 1 second to finish the arithmetic here, and then I'll address that question in chat. If I factor 5/2 cubed out from this expression, I'll get negative 2/3 plus 1 times 5/2 cubed. And negative 2/3 plus 1 is 3/3, so minus 2/3 is 1/3. So this is 1/3 times 5/2 cubed. And I think that's as nice as that's going to get. The integration step here, where I pass from here to here, we're increasing the power of y by 1 and then dividing by that new power. So the y squared, when I integrate, will go to a 1/3 y cubed, right? Y cubed because I increased the power by 1, and then I need to divide by that new power. So that gives me a copy of 3 downstairs. The -2 comes along for the ride. And the same sort of thing happens here. I increase this power of y by 1, so it goes from y to the 1 up to y to the 2, but I also need to divide by that new power, and the 5 just comes along for the ride. Okay, so that was addressing an earlier question in chat. And then Margaret asked a nice question. At the end of a problem, what do we do? Periods are good. I like periods. Yep. Says, you know, we're working in a full sentence. This leads to this, leads to this, leads to this, and then full stop. If it happens to be the case that you're proving something, Paul Hallmush introduced this notation called a tombstone. So if you finish a problem and it is equivalent to a proof, this stands for QED, or that which we wanted to show. But a period is sufficient if you're just calculating. I don't have a strong preference one way or the other, but I do think you know, notation matters. And definitely if you're finishing proving something, the box is a nice notation to use. But otherwise, you know, whatever, full stop is fine. Full stop is fine also. Okay, questions on this guy? Feeling mostly comfortable? I think Patanji asked for a couple other problems, 21 and 25. So let's take a look at one of those. Let's see, 25 we actually haven't talked about, so we're not ready for that yet. I'll be introducing that material today. But we can take a quick look at 21 here, which asks us to find the area bounded by these two curves. Sketch the curves, find the area. They also want us to draw in one of those little Riemann rectangles. There's a reason for that. It's because in the next section, when we start talking about volumes, drawing in these little rectangles is going to actually be pretty important. So this will be our last example problem for the day. Last homework problem, sorry. So we're going to find the area bounded by these two curves. Well, this is definitely just a line to the origin with slope 5. This quadratic is a parabola. I can factor it to help me see what it looks like. So it opens up because the coefficient of x squared is positive. And it has roots at 0 and 2. So I'll mark this as like 1, 2. So this whole affair looks something like this. And then y equals 5x. It's a straight line through the origin with slope 5. So my region should look something like this. This is y equals x squared minus 2x. This is y equals 5x. So my upper function here is definitely the line, the y equals 5x. My lower function here is definitely the quadratic, y equals x squared minus 2x. And because these are both giving y as functions of x, the most natural thing to do is to set this area problem up as a dx integral. if I wanted to draw in one of my little approximating rectangles, one of my little Riemann rectangles, or one of my little differential thickness strips, it would look like this. Now you can plop those wherever you want. You can drop them down wherever you like. The purpose of having you draw the strip on this problem is to just remind you that your integral is going to be done dx, because this strip sweeps out this area as it moves from left to right. If I drew it over here, it would be very short. And you imagine this strip moving through this region, each of those strips having some tiny little area, and when you add up all of those areas, or when you let that strip sweep all the way through that region, you get the entire area we're trying to calculate, which is definitely this. And soon, Monday of next week, I'll be asking you to imagine like rotating this whole region, say around the y-axis. If you spun that whole region around the y-axis like it was on a barbecue spit, this would sweep out a solid. It would sweep out an object that has three-dimensional measure. It has a volume, and we're going to start finding the volumes of those solids. It can be a little bit complicated, but the way you get there is by imagining just the strip itself rotating, and that would give you like a little cylinder, if just the strip itself rotated. And then we'll do the same sort of thing where you integrate the result from the strip to get the whole thing. So here my area. Well, we still need to do one other thing. We need to find these intersection points. So before I start on the area, I need to find the intersection points, which will be the bounds for our integral. So to do that, I'll set x squared minus 2x equal to 5x. I can pull the 5x over, and I get x squared minus 7x equals 0. So that factors as x times x minus 7 equals 0. So these intersect at x equals 0 and x equals 7. So that tells me that this guy right here, that's x equals 7. This guy over here is obviously x equals 0. So my integral will look like the integral from 0 to 7 of the upper function here is 5x minus my lower function, which is x squared minus 2x. And this is all being integrated dx. If I distribute that negative, combine like terms, I'll have negative x squared. And then 5x minus negative 2x is 5x plus 2x is plus 7x. And again, the antiderivative step here just follows from the power rule. So I won't have my integral anymore, sorry. I'll increase the power by 1 and divide by that new power. So this will be negative x cubed over 3, or negative 1/3 x cubed, plus increase the power by 1. So this will be an x squared, but then I need to divide by that power. So it'll be plus 7 halves x squared. And this is all being evaluated from 0 to 7. At the lower bound 0, both of these are 0, so I don't have to worry about that. But at the upper bound 7, I'll have negative 1/3 times 7 cubed plus 7 halves times 7 squared. So that is negative 7 cubed over 3 plus 7 cubed over 2. So I would factor the 7 cubed out again. And you'll have negative 1/3 plus 1/2. So that's 7 cubed times, what is this? As a ratio over 6, this is 2/6. This is 3/6. So negative 2 plus 3 is positive 1/6. So you get 7 cubed over 6. And I would be fine with you leaving it like that. I'm not particularly interested in seeing you do the arithmetic to evaluate 7 cubed as an integer. It's 7 cubed. You know, that's a perfectly fine way to write it. Questions on this fella? Okay, so my hope is that by spending the first week working these kind of simple-ish problems, right, the area problems and the use sub problems, that we all come to a kind of common basis of knowledge, whether your Calc 1 class made it through this stuff or not. I don't want that to affect you moving through our course. So if you were not comfortable with use sub in the past, I hope that you are getting more comfortable with it now. It is something that will require quite a bit of practice. Even with a good amount of practice, not everybody is amazing at it right away. So don't feel bad if it's a little bit intimidating sometimes, but do make sure you work on it until it feels good. That's the important thing. And if you want to talk about some use sub problems, or if you want to talk about some problems from Calc 1, or anything that you feel is holding you back or is not as good as it could be right now at the start, these are the right times to be doing that. Don't wait till the middle of the term to say, I don't really understand why we change bounds, or I don't really understand how we're calculating these differentials. Come see me in office hours today and we can work through that, and then it won't sit so heavy on you all through the term. There is one bit of new material that I wanted to introduce today, and that's the concept of average value. So this is going to be section 6.5. It just doesn't fit anywhere else in the course. It's not related to areas, and at least not directly related to the types of area problems that we're trying to solve. It does have to do with integrals. So certainly there is an interpretation having to do with areas. But really, this is a concept from statistics. So section 6.5, average value. If I gave you a bunch of numbers and I asked you to find the average, so if I asked you to find the average of the numbers y1, y2, y3, say maybe I have n of them all the way out to yn, how would you do that? Well, this is something we all learned in grade school. You add them all up and then you divide by the number of numbers. In statistics, we use the bar notation for the mean. So the particular kind of average we're looking at here is what's called a mean, M-E-A-N. And it would be the sum, y1 plus y2 plus y3, all the way out to yn, all divided by n. And then the question becomes, well, what if you wanted the average of all the outputs of a function f of x? This formula works great if you only have finitely many things. Say function of x from x equals a to x equals b. So let me draw the picture. Here's your function f. Maybe here's a, and here's b. So rather than having a finite list of y values that I can add up and then divide by the number of them, I want to know if I take every single y value on this graph between a and b, how do I find the average of all those? And there's definitely infinitely many of them. There's one for every number x between a and b here, because the graph is continuous. There's too many. It's infinitely many. In fact, it's a big infinity. And that might be a weird sounding thing to say, but I promise you there's more than one infinity. Some are larger than others. This turns out to not just be infinitely many y values in here. There's a genuine ass load of them. There's a big infinity of them, Aleph1 of them, rather than Aleph naught, which is what most people think of as infinity. So I clearly cannot form something like this, right? I can't possibly add all these up and then divide by the number of them, because the number of things I'm adding up would be infinite. And then I would be dividing by infinity. It just wouldn't make sense. But we do have a notion of summing all the values of a function. It's called an integral. That's what your integral does. So I want to show you in the textbook because I think it does a little better job illustrating some things. So this is the idea here. Your normal concept of average is the one that we just showed. If we wanted to find the average for all the values of a function between a and b, you can chop that up into a bunch of subintervals and then start building a Riemann sum. And that's precisely what they do here. So let me try to help you see this here. So we can chop this up into a bunch of subintervals. So this would be x1, this would be x2, this would be x3. A is x0. I'll call this xi minus 1, and I'll call this xi. And we build a Riemann sum, right? So I want to take the average of all of these it starts to look very Riemann summy. This first guy right here would be f of a. This guy right here, his y value is f of x1. This guy right here, his y value is f of x2. So these y values, this would be f of xi, this would be f of, xi minus 1, f of xi. So the average is approximately f of x0 plus f of x1 plus f of x2. The middle here looks like f of xi minus 1 plus f of xi. And you go all the way out to f of b, which is f of xn. We usually call this guy xn. I think your book uses a lowercase. And then we would divide by the number of things here. And in this case, it's just n. So I've chopped that up into n subintervals. So here we chop the interval AB into n subintervals of length b minus a over n. We call that delta x. And then you can just massage this algebraically until it turns into a Riemann sum, right? So if I write this in sigma notation, that's sigma I from 0 to n f of xi. And it's all being divided by n. That's the same as multiplying by 1 over n. And this looks very much like a Riemann sum, right? If I multiply and divide by b minus a, then I can group this b minus a with this 1 over n to form a delta x. And I can bring the copy of b minus a from the bottom out front. So this is 1 over b minus a times capital sigma I from 0 to n f of xi times b minus a over n. Now this piece, this is delta x. So this thing is looking like a Riemann sum. This is equal to 1 over b minus a times the sum from I equals 0 to n f of xi times delta x, which we recognize as a Riemann sum for the integral to 1 over b minus a out front, integral from a to b, f of x dx. And this is what we define to be the average value of the function f of x on the interval AB. So if the Riemann sum work is terrifying to you and you hate it, try not to hate it so much. We will be working a lot with this capital sigma notation later in the term, that summation notation. That is hugely important down the line. Remember, it's just a nice, convenient way to write big addition problems. So this is f of x0 plus f of x1 plus f of x2 all the way out to f of xn. That's the same as capital sigma I from 0 to n f of xi. So this numerator in summation notation is just this piece. The n downstairs is the same as multiplying by 1 over n. And this piece I introduced later. So right now, we should be able to see that this line collapses into this when we write it in sigma notation. And then we multiplied and divided by b minus a because I wanted to introduce this delta x. Once we write it like this, that should jump out as a Riemann sum to us. It looks just like the Riemann sums for integrals that you learned about at the end of Calc 1. In fact, it can be even symbolically translated over into the integral very nicely. The 1 over b minus a just comes along for the ride. The capital sigma here, which is a Greek letter s, turns into the integral, which is a Latin letter s. F of xi is f of x, delta x becomes dx. So this is the formula for the average value of a function f of x over the interval ab. What Nicholas said in chat there is pretty much correct. My only caveat would be that we're not actually going over all the x values in the interval. We're looking at finitely many x values in this interval. Right, there's exactly n of them, or n plus 1, I guess, from x0 to xn. There's n plus 1 terms in this sum. So not infinitely many, but you can think of it as like taking a sampling of x values from down here, which gives us a sampling of y values from up here. And then as we send n to infinity, this sum turns into this integral. And now this really is adding up all the y values that are output by f of x from a to b. That is the most natural interpretation of the integral. This is all well and good, but what the hell do we do with it? So I've scared you with some capital sigma notation, but have I really taught you anything yet? Well, I don't know. So there's another way to interpret this. First, this is the formula, the recipe that you need to solve the homework problems, right? I just ask you to calculate the average value for a few different functions, nothing wild there. So you just compute the integral from a to b, and then you divide by the length of the interval. Okay, so maybe here's a, here's b. And we know that the integral from a to b, forget about the 1 over b minus a, we know that the integral from a to b is just the area, right? What happens when you divide by the length of that interval, this is a constant. The name of this constant, I should say, is f av. That's the notation the book uses. And it's just a number, right? 1 over b minus a times the integral from a to b of f of x. This is a number. This is a number because it's a definite integral. So this whole thing, the average value, is just a number. It's one number. So you give me a function in an interval, I can find you that number. One way of interpreting that number, you can say that this is the unique constant function that bounds the same area as f over that interval. So if this is f of x, I'm going to draw in another function now. Something like that. Which will be a constant function. And I'm just guessing on this. This is f av. And the idea is that this constant function bounds the same area as f over the interval ab. So if you look at the area of this area bounded by f on ab, I'll draw that in like this. Really, I need more color. So there's the area bounded by f. And what you'll notice is that that area is equal to the area of this rectangle. So the purple and black areas are the same. Seems like color might not be coming through so well here. The area of this rectangle is the same as the area underneath the curve. Area in the rectangle defined by F is equal to the area bounded by f of x on the interval AB. So I might pull up the picture in your book so you can get a better idea, because I know the color isn't coming across so well. But you can think of average value as being the unique constant function that bounds the same area as the not necessarily constant function f of x. Here you go, this is the picture. So the gray area here is the same as the blue area here. So this average value, this red constant, tells you the y value, the height of the unique constant function that bounds the same area. There's also a way of thinking about this in terms of the mean value theorem. Okay, so let's do a little bit of calculation. I have you guys for just a few more seconds, and I think Hotanji wanted to see number 25. So let's take a look at 25, because that's also a good substitution problem. So again, the parts you need to solve the problems, just this. But this interpretation is nice, especially when you think about the mean value theorem. We'll talk more about the mean value theorem for integrals a little later in the term. Remind you the connection to average value then. But the big deal here is that statistically, if you had a uniform, or if you had a continuous probability distribution, if you had a probability distribution function that was not discrete, right, did not come from a particular set of finite values, but instead your possible outcomes ranged over an infinite set, this is how you would find the expected values, by doing an integral. So for example here, let's find the average value of f of x. I think it was e to the sine x times cos x. Yeah, or e to the, they used a t, I'll use an x. E to the sine x times cos x over the interval what do we want, 0 to pi over 2? Yeah. Like that. So we know that the average value, f av, is always 1 over b minus a times the integral from a to b of f of x dx. So here, f is the function e to the sine x times cos x, and a and b are the endpoints for this interval. So this is 1 over pi over 2 minus 0 times the integral from 0 to pi over 2 e to the sine x times cos x dx. Did you find it? This number I can clean up, and I'll clean that up in the next step. Don't panic about that. But the challenging thing here is this integral. So how do we handle this integral? Margaret's suggesting a substitution. What kind of substitution? What should we sub for? Very good. Yeah, Margaret 1 nailed it. Here, if this was just e to the x, I know how to integrate that, but e to the sine x looks freaking weird. I would love to get rid of that sine x. So I think maybe I should try to substitute for him. And then I ask, do I have the necessary pieces in my integrand? Do I have the derivative of sine x, or at least something close to it floating around? Yes, yes I do. I've got this cos x right here. So I'm going to make the substitution. U equals the sine of x. Du then is cos x dx, and that's convenient because I have a cos x dx right here. The other thing I need to do, because I'm making a substitution in a definite integral, I have to change the bounds. So my old lower bound was x equals 0. When x is equal to 0, what is u? Well, u is the sine of x. So when x is 0, u is the sine of 0. The sine of 0 is 0. So my new lower bound is also 0. My old upper bound was pi over 2. So when x equals pi over 2, what is u? Well, u is the sine of x, so it'll be the sine of pi over 2, and the sine of pi over 2 is 1. So my new upper bound is 1. Amy, it's okay, come on. Hey, good boy. It's all right. It's all right. So my new integral, let's go ahead and clean up this constant out front. Pi over 2 minus 0 is pi over 2. 1 divided by pi over 2, that's 2 over pi. And then we'll have integral, now going from 0 to 1 rather than 0 to pi over 2 because we've changed our bounds. E to the sine x, that's e to the u. And cos x dx, that's exactly du. So this becomes a much nicer integral. An antiderivative for e to the u is what we need now, and that's not hard. It's just e to the u. So remember, exponentials have themselves as their derivative, so necessarily they have themselves as their own antiderivative also. And I evaluate that between these new bounds. We do not go back to the old variable. Because this is a definite integral with bounds, and because we changed these bounds as we went along, there's no need to go back to the old variable. I just evaluate this function between these numbers. So this will be 2 over pi times e to the 1 minus e to the 0, which is the same as 2 over pi times e minus e to the 0 is 1. And that's it. So the average value is 2 over pi times e minus 1. Questions on this problem? Questions on average value in general? There's really not much to it. Finding the average value is exactly as hard as finding the integral. And you just have to divide by the length of the interval. Since we do still have 15 minutes left in class, I want to practice a little more some challenging U sub problems. So I'll give just a second longer for anybody who's writing here. Make sure you get this stuff in your notes. Again, I really want to encourage you to organize your work the way I organize my work here. It makes it nice and readable, but also it'll help you locate mistakes if you make them. It'll make it easier for me to grade. And it'll also get you into good habits. And you want to be developing good habits right now, because very soon this class is going to get quite hard. And if you have these good notation habits, it'll save you quite a bit of stress in the near future. Okay. So some fun U-sub stuff. Some more practice with substitution. Margaret, no, I don't have a particular preference for colors. So this looks like a blue pen, but it's actually a G2 purple refill. So as long as you don't use this purple color from Pilot, I'll be perfectly happy. And honestly, even if you do, I've got other colored pens. But right now I've got a big stock of these purple G2s. So on exams, if you could write in something other than a purple Pilot G2, that would be nice. That way I don't, because I'll be printing your written work and marking it up with comments, it would be nice to have it not be that same color. But besides that, I really don't care what color you write in. No, it's fine. Whatever you'd like. This is a fun integral. Does anybody have any idea what I could do with this thing? Something to do with E, yeah. So one of the reasons I like this is because it requires you to be a little bit careful with your exponents. If I use e to the 2x as my u, let's see, so what would happen if I try, I'm gonna use the symbol z here, because this is a habit that starting next week I'm gonna be in, and I would like you guys to get in this habit also of using a variable besides u for your substitutions, because we're gonna use the letter u to mean something specific in the future. So I'll try z equals e to the 2x. Then dz would be what? What's the derivative of e to the 2x? Not quite. So e to the ax all primed will always give you e to the ax times a. It's a chain rule thing. And because it's an exponential function rather than a power function, we don't use the power rule. We're not like subtracting 1 from the power or anything like that. E to some stuff always differentiates to itself times the derivative of that stuff. And more generally, e to the u of x, if u is a function of x, will always differentiate to e to the u of x times u primed of x. So here my dz would be 2e to the 2x dx, which isn't the end of the world. Yeah, so here I see a few correct suggestions in chat there from Quintang and Margaret. So here, what's the problem with this substitution? It's a good guess. It's a reasonable guess, and I wanted you guys to make a guess like this so we could talk about this, because we haven't, every example of substitution we've done in class went through beautifully. We didn't have any issues. But here there are issues. If I wanted to try and make this substitution go through, I would need an e to the 2x that I could group with my dx. But I don't have that. I have an e to the x that I could group with my dx, but I don't have an e to the 2x here. So I don't have this. In my integrand in a way that's free to group with the dx. I want to even go a little bit further. Some people prefer to solve this relationship for dx and try to plug it in. My bounds would change, so I'll go ahead and show you what the bound changing would look like. When x is 0, z would be e to the 2 times 0 is 1. And when x is 1, sorry, when x is 0, when x is equal to 1, z would be e squared. So if I try to make this substitution go through, it would be the integral from 1 to e squared. I have my e to the x up here. I would have 1 plus u down here. And then if I solve that for dx, it would be equal to dz over 2e to the 2x. So I would have dz over 2e to the 2x. And I could try to make this work. I could bring out a 1/2. And then I would have 1 over e to the 2x dz. But the challenge here, the issue, is that these don't cancel perfectly. I could write this as e to the x times e to the x and then cancel one of them. Oh, I wrote a u here, didn't I? This should be a z, sorry. Bad habits. I know this might seem like I'm harping, but I really do want you guys to think along with me about why we have a hard time making this substitution work. This would be e to the x over e to the x times e to the x dz, and I can cancel one of them, but I would still have a factor of e to the x downstairs that I can't get rid of. And there's absolutely nothing I can do here. I cannot integrate this. I can't do shit until I get rid of all the old variables. Remember, that's the cardinal rule of substitution. We talked about that on our very first day. Anytime you make a substitution, you have to get every single piece of the integral transferred over into the new variable. It means you got to change your bounds. It means anywhere you had an x in your original guy, you got to replace it by whatever the new variable is. You got to swap everything over. And this piece is fine. 1 over 1 plus z, that doesn't have any problems. The dz is good, but I still have a 1 over e to the x. You could try to come back here and rewrite this. You could try to solve this for x and then plug that in for this x down here. That sort of maneuver is useful sometimes. But here it's just not working nicely. It just doesn't look good. I cannot from here do anything. I can't pop this out because it's not a constant. I can't do any of the integration with this piece because I still have this old variable piece floating around. So this is what it looks like when a substitution doesn't go well. And I think it's important that we see that. You can try to make it go through. And there are tricks I'll show you to make things like this go through. But when you see something like this not working out super nicely right away, it's a hint that you should try something else. So if I come back to the original problem and rewrite as Margaret and Katong suggested, this is integral 0 to 1 e to the x over 1 plus e to the 2x is e to the x squared. This is because we have this algebra rule that says a to the b all to the c is the same as a to the b times c. It's a rule for exponents. So yeah, Margaret, it absolutely does do something. This is really nice because now I can substitute z equals e to the x. Because dz there would be e to the x dx, and I do have a copy of e to the x floating around. I didn't have a copy of e to the 2x floating around. Still need to change my bounds. When x is 0, z would be equal to e to the 0, which is 1. And when x is 1, z would be equal to e to the 1, which is e. But this substitution will work really nicely. New integral goes from 1 to e. The e to the x dx, that's dz. So I just get 1 over 1 plus z squared dz, like this. And that is, again, arctan. And we evaluate from 1 to e. So this will be the inverse tangent of e minus the inverse tangent of 1. And the inverse tangent of e, I have no idea what that number is, but we should all know what arctan 1 is. What is the inverse tangent of 1? The tangent of what angle between negative pi over 2 and pi over 2 is equal to 1? Good. So this is the inverse tangent of e, whatever that is, I just leave it as it is, minus pi over 4. Okay, this is a good problem, and I'm glad that we were able to see something not work out beautifully, because it's important that you're able to recognize when these things aren't going well, so that you know to go back and try something else. I do also want to show you an instance where you can force something through, even though it doesn't look like a perfect substitution. So after this guy, I will take a few minutes to do that. Questions on this correct solution to this problem? Any of the algebra steps or calculus steps here that we want to talk about? Okay, so then the last thing I want to do is show you how you can make something like that actually go through if you have to. I'm not going to do it for that particular problem because it's not a good move. But can we make the sub z equals, let's try it like ln x in, say, integral 1 to e sine of ln x dx. So the challenge here is, again, the differentials not being nice. If I try to sub z equals ln x, then dz would be 1 over x dx. And I do not have a 1 over x anywhere in my integral to play with. I'll calculate the bounds while we're here. When x is equal to 1, z is equal to 0. The natural log of 1 is 0. When x is equal to e, z is equal to 1, because that's the natural log of e. And we can try to make this go. I'll have integral 0 to 1, sine of ln x. Okay, ln x is z. But then dx, if you solve this for dx, you get that dx is equal to, multiply both sides by x, it's x times dz. So dx here is x times dz. Hammy, it's okay. And the problem, of course, is that I've got this mixture of variables. Hammy, stop. Sit. It's okay. The sine z, this piece looks okay. The dz looks okay, but I got to do something with this x. I still have an x floating around. It's the same sort of problem that we had when we had tried the other substitution on the last integral. It's that all the x's didn't go away. What you can do in this case, and what you can do in general when you run into this problem, is go back to your substitution. Z is equal to the natural log of x, and solve that for x. So how do you solve this for x? You got to get x out of the natural log, so you exponentiate on both sides, base e. So you learn that e to the z, e to the ln x, that's just x. Okay. So this x piece that we weren't able to get rid of, I can actually rewrite that as e to the z. So this would be sine z times e to the z dz. And right now you guys don't know how to do this integral, but soon you will. When we talk about section 7.1 on integration by parts, I will show you how to do this integral. It's a good integral, it's a challenging integral, it's a lot of fun, but it's not easy. And so if you wanted to attack this integral, you would first make a substitution like this. Even though at a glance, it doesn't appear to work because you have this x that's stuck. But you can get around that by going back to your original substitution equation, z equals ln x, that's what we chose for our substitution, and solving it for the original variable. That will let you take care of any lingering bits of shit that have not gone away. Now the substitution problems I've assigned you for homework, I think there are not any, or if any, at most one problem where not everything cancels right away, where not everything is perfect right away with your substitution. But when you do have that situation, if you know you want to make that substitution, that you chose the substitution correctly, but when you plug everything in, you still have some x's or whatever your original variable is floating around, this is how you get around it. You go back and solve your substitution for the original variable. That'll take, okay, everywhere you have an x, you can just write e to the z instead. And that will get rid of whatever x's are left. Make sense? All right, so I hope we're all feeling like wizards when it comes to use substitution. Badass integrators, unstoppable. Turns out there's lots of other nice, sneaky integration tricks, and we are going to start learning those, not next week, but the week after. Next week, we're going to focus on volumes. So I'll be giving you regions like this. Maybe I give you something like this. A semicircle. If we rotated that about the x-axis, if you imagine I can pick this up and spin it like that, it would sweep out a sphere. And we'll see how to find the volume of the sphere that sweeps out. If you were to spin it about the y-axis, if you were to spin it like this, then it would sweep out kind of an upper half of a donut. And we'll see how to find volumes of things like that. So next week is going to be more geometry stuff. It's kind of in line with the area problems we've been doing. And then the week after, I'm going to start showing you how to integrate hard things like this. That's where we're going. But right now, it's important that you just finish up this week's homework. Stay enthusiastic about the class. Make sure you're working hard. Make sure you've got everything sorted out. If there are any other homework problems that you're stuck on, please come see me in my office hour this afternoon. I have an office hour from 3:30 to 4:30. And that is it. You've made it through the first week of Calc 1, Calc 2, just 14, 15 more to go, and you'll be good. So I hope you guys have a lovely rest of your day. And if you would like to talk more, come see me in my office hour later. Otherwise, I'll see you guys all on Monday.